All right, let's go ahead and get started. I do want to welcome you to Unit 16. This is Reaction Kinetics. Folks, the purpose of these notes is to shed some light on Chapter 12 of the Zoomdoll book. If you would like to follow me along with me in Zoomdoll, this is Reaction Rates 12.1. So here we go. So let's start with the question of why chemical reaction kinetics or chemical reaction kinetics is important. And the answer has to do with, in large part, commercial reasons. Let's take a look at this process right here. It's called the Homber process. This was a process that was invented by Franz Haber just prior to World War I, and actually he was trying to invent a way of manufacturing nitrogen for explosives, but what he came up with instead, ironically, was a way of creating massive amounts of ammonia, which is an important component of fertilizer, and he ended up saving, in this process called the Homber process, millions of lives that would have otherwise been lost to drought because of the ammonia that was produced. The Homber process became known the world over as a process that saved many lives. So, what is the Homber process, and why is it important to us in chemical kinetics? Well, as you can see here, we have N2 plus H2 forming NH3. So the ammonia is what we're interested in. But as it turns out, this is a reaction that is very spontaneous. In other words, it has a delta G that's very negative. And by the way, if you haven't gone through those videos on thermodynamics, you should do that before you begin this process of reaction kinetics. Delta G being negative means it's a very highly spontaneous reaction. It's going to happen. But that doesn't necessarily mean it's going to happen fast. So the chapter really begins with this idea that spontaneity really must be separated. The idea of spontaneity must be separated from a fast reaction. The Homber process, say for example at 25 degrees room temperature, is not a fast process at all. Even though it's highly spontaneous, it's not a very fast process at all. Now, as it turns out, it becomes very commercially viable if you increase the temperature significantly to say to 300 degrees. But you're also going to need a catalyst, and we'll talk more about catalysts later on in this unit. But the point is that don't assume that because something is spontaneous that it's going to happen fast. It's not necessarily a direct correlation. So let's take a look now at another reaction, and this is the decomposition of NO2, nitrogen dioxide. This is an important pollutant, and it will decompose into nitric oxide and O2 in this process right here. So notice that it is a 2 to 2 to 1 mole-to-mole-to-mole relationship. And what we want to talk about, and use this reaction as kind of a model for how reaction kinetics, or how fast a reaction goes. So we can talk about, for example, on the left side, the degradation of NO2 and its conversion into other things, or we can talk about the creation of nitric oxide and the creation of oxygen gas. Now, let's take a look at this table. This is a table of the concentrations of reactants and products as a function of time for the reaction. So here's the reaction. We've got NO2 becoming NO plus O2, right? So that's the reaction. Again, it's a 2 to 2 to 1 mole-to-mole-to-mole relationship. So let's take a look at what's happening to the NO2 over time. So if we look at time 0 and compare it, say, to time 400 seconds, what we see is that the amount of NO2 present, say if we had a vessel at a certain temperature, a closed vessel, that the amount of NO2 present is decreasing, right? It's getting smaller and smaller and smaller. But if we look at NO, it started at 0 and got bigger and bigger and bigger, and the same is true of O2. So why is that the case? Well, it's because the fact that, again, this is a degradation experiment. In other words, NO2 is exiting, its amount is getting less and less, and NO and O2 is increasing as that is happening. So let's take a look at what that might look like in a graphical form. So you can find this in your book. It's much more accurate than mine is here. I just have a simple drawing here. But this you can find in your book on page, page 554, and I would encourage you, by the way, to look this one up because it is an important relationship. So what we have here is on the x-axis time and on the y-axis concentration. So that's how we measure the amount of something in terms of concentration in moles per liter. So what we saw in the table is what we see now graphically. Remember that NO2 was the reactant, that nitrogen dioxide was a reactant, and it's degrading. So over time, what happens is that the amount of NO2 decreases more and more and more. Now both NO and O2 increased. Now I want you to notice that O2 increases a certain amount, but NO increases twice the amount. Let's go back up to the reaction and see if we can explain why that might happen. So here's a reaction. Remember, it was this relationship here. It was twice as many moles of NO are produced per mole of oxygen gas. So if 1 mole of oxygen gas is produced, 2 moles of nitrogen dioxide or nitric oxide are produced. Okay? So that would explain why then, on this table, or this graph, I should say, that we see that NO is approximately twice as tall at some advanced time as O2, right? Nonetheless, the overall picture that we should be getting is that NO2 is decreasing, NO increasing, O2 increasing, but not as much. Now, we can talk now about what we call an instantaneous rate. And I've used a black line to denote that. In fact, Zumdahl looks at a particular time. That's time t equal 100 seconds. My scale is not the same as the Zumdahl book, but if we look at time t equal 100 seconds, what we can see is that I placed a tangent line. Now that tangent line tells me the instantaneous velocity or speed of the reaction at that point. That's the speed at which NO2 is changing at time equal 100 seconds. Now, the reason that's important is because of the fact that if we look at this table, we can talk about the fact that, let me just scroll down here just a bit. This is the average rate in moles per liter per second of decomposition as a function of time. Now what I want you to notice that over a period of time, this by the way is table 12.2, over a period of time, the rate of change of decomposition is decreasing, right? Note that the rate decreases with time. Well, that makes sense. Why would that make sense? Let's think about this. Well, remember that the reaction that we have is one in which we've got, I'll write this right here, we've got NO2 decomposing into NO plus O2, right? And that was, NO2 was decomposing, NO was being formed, and O2 was being formed as well. But remember that the degradation of NO2 and the reaction moving in the forward direction is going to be dependent upon NO2 molecules banging into each other. Well, it only stands to reason that as time goes on, those NO2 molecules are going to be present in fewer numbers, and there's going to be less of them to bang into each other. So the amount or the rate at which NO2 is disappearing is going to be decreasing over time. Now let's talk about rate in general. If I were to say that A with brackets around it was equal to the concentration of some product or reactant, we'll call it A, in moles per liter, then rate then would equal to the concentration at some time, we'll call it T2, minus the concentration at another time, we'll call it T1, over the difference in those times. So let's take, for example, NO2. So NO2, we'll look at the first 50-second time span, right? If we look at that first 50-second time span, what we'll see is this, and I'll take us both back to the table. In this first 50-second time frame, obviously 50 seconds is going to elapse, but we're going to go from 0.0100 to 0.0079 moles per liter. So the difference in concentrations then is going to be let me take us back to where we were originally. The difference then is going to be, this is going to be, well, I'll just let you subtract it on your calculator. At any rate, when I divide it by 50 seconds, I get this number. That's a negative 4.2 times 10 to the minus 5 moles per liter per second. So in other words, for that first 50-second period, on average, the amount or the concentration of NO2 is decreasing by negative 4.2 times 10 to the minus 5th moles per liter every second, right? Now, what we like to say about rate is that rate is always positive, because when you think about it, you know, if you think of, for example, an automobile that's moving in the forward direction, that automobile is going to have a positive rate. So even though we got a negative sign here for this value of the rate, we like to switch that to the negative of that value. In other words, a positive value, because the fact that we say that rates are always positive. So we'll put a negative in front of that value. When something's diminishing or going away, we're going to put a negative in front of that, and we're going to call it a positive. So the rate at which NO2 is degrading then is 4.2 times 10 to the minus 5th moles per liter per second. All right? All right. We've already covered this table right here. We've talked about the fact that average rates are decreasing over time for NO2, right? Okay. Let's talk a little bit about slope, and I've already alluded to instantaneous rates, right? But if I take a tangent to the line at any point, and again on the curve, we took a look at t equal 100 seconds. Remember that slope is equal to the change in y divided by the change in x, right? So if we look at, for example, the rate of degradation of NO2, if I look at, say, 110 seconds, right? Then the difference in concentration of NO2 is going to be 0.0026. By the way, I have a typo on your sheet. If you would change that to 0.0026, I think there's probably 3 zeros on your sheet. Make it 0.0026. So therefore, the rate would be, and we'll make it the negative of that, 2.4 times 10 to the 5th moles per liter per second. And I'll let you do that on your calculator. All right, so now, if we were to look at the slope of the tangent lines for NO and O2 respectively at, say, 250 seconds. So you just look at 250 seconds, and we'll go over a 70-second time span. What we're going to find is that we come up with these rates: 8.6 times 10 to the minus 6 moles per liter per second, and 4.3 times 10 to the minus 6 moles per liter per second. Now that's important because of the fact that from the balanced equation, we can see this. From the balanced equation, we can see that the rate of consumption of NO2 is equal to the rate of production of NO, which is equal to twice the rate of production of O2, right? Because remember, it was a 2 to 2 to 1 mole to mole to mole relationship. So to get the production of O2 up to the production of NO, we're going to have to multiply it by 2. So we have the change in NO2 concentration divided by delta T is equal to the change in NO divided by delta T, which is equal to twice the change in O2 times delta T. So that'll do it for 12.1. I'll see you in the next one.